Welcome to Biostatistics. Imagine you buy a brand new smartphone. The moment you turn it on, a hidden timer starts ticking down to the exact second it will eventually break. In biostatistics and engineering, we call this ticking timer the survival time. Because we cannot predict the exact future, this time is random. Today, we are going to learn about the functions of survival times, which are the mathematical tools we use to understand and predict these random lifespans. Now that we understand what survival time is conceptually, let us look at how it applies to the real world. Survival time is simply the amount of time that passes before a specific event happens. This event could be a machine breaking down, a patient recovering from a disease, or a light bulb burning out. Because we cannot predict the exact future, this time is random, meaning it follows certain rules of probability. These functions help us answer critical questions like what the chance is that a phone lasts more than 2 years, or how much risk it faces right now compared to when it was brand new. To answer those questions, the most fundamental tool we use is called the survival function. Think of a group of 100 patients starting a clinical trial. The survival function tells you exactly what fraction of them are still alive and doing well at month 3, month 6, or year 5. It is the ultimate measure of lasting power. Logically, at day 0, nobody has failed yet, so the probability is 100%. As time goes on forever, eventually every machine breaks and every organism passes away, so the probability drops to 0. It is a strictly decreasing curve because once a failure happens, it cannot be undone. Let us look at the mathematical form of this concept. The survival function, S of t, is the probability that the actual failure time, capital T, is strictly greater than our target time, lowercase t. This is closely related to the cumulative distribution function, or CDF, written as f of t. The CDF measures the exact opposite, the probability that the event has already happened by time t. Because a subject either survives past time t or fails by time t, these two probabilities must perfectly add up to 1 or 100%. So, if you know the CDF, you can always find the survival function by simply subtracting it from 1. While the survival function looks at the big picture of lasting a certain amount of time, we also need to understand the immediate danger. This brings us to the hazard function. The hazard function is the instantaneous failure rate. It measures the immediate risk of failing in the next tiny fraction of a second, assuming you have already survived up to this exact moment. Think of it like the speedometer in your car, which tells you your exact speed at one specific instant, not your average speed for the whole trip. If a patient has survived exactly 5 years after surgery, the hazard function tells the doctor how much immediate danger they face on that exact anniversary. This speedometer of risk has a very specific mathematical definition. The hazard function, h of t, is calculated by dividing the probability density function, f of t, by the survival function, s of t. The numerator represents the unconditional, overall rate at which failures are occurring in the entire population. But we only care about the people who are still alive. So by dividing by the survival function in the denominator, we adjust the risk to only count those who are still at risk. This perfectly captures conditional probability, the chance of failing right now given the condition that you have survived until now. Note that because it is a rate, its value can sometimes be greater than 1. If the hazard function is the speedometer showing your immediate risk, we also need an odometer to show the total trip. That is the cumulative hazard function. It adds up all the instantaneous risks from the very beginning of time all the way up to your current time. Imagine walking slowly through a radioactive room. The hazard function is how much radiation is hitting you at one specific step, while the cumulative hazard is the total dose of radiation your body has absorbed since you walked in the door. By adding up all these tiny slices of immediate risk, we get a complete cumulative picture of the total danger the subject has faced over their lifetime. To add up these tiny slices of risk over a continuous period, we use calculus. The cumulative hazard function, capital H of t, is the integral of the hazard function from time 0 to time t. Inside the integral, h of u is the instantaneous hazard at a dummy time variable u, and du represents a microscopic slice of time. The integral sweeps from time 0 to time t, gathering up every bit of risk along the way as a mathematical vacuum cleaner. As time increases, this accumulated risk can only grow larger or stay the same. It never decreases. Now that we have defined both the survival probability and the accumulated risk, a beautiful and deeply important mathematical relationship emerges between them. The total accumulated risk directly dictates your actual chance of survival. This is the absolute cornerstone of survival analysis because it allows you to calculate exact survival chances as long as you know the history of the risks faced. It perfectly translates the odometer of risk into a concrete percentage of survival. Let us look at the master formula that connects them. This is our final magical result. The survival probability at any time t is equal to the exponential of the negative cumulative hazard. As the total accumulated risk, capital H of t, gets larger and larger, the negative sign in the exponent ensures that the survival probability shrinks closer and closer to zero. This single equation bridges the gap between the immediate dangers a subject faces and their long-term probability of making it through. Before we prove why this works, let us see this formula in action with a concrete example. Let us look at a specific type of industrial light bulb that has a constant instantaneous failure rate of 0.1 per year. This means the hazard function is a flat number, 0.1. The risk does not depend on time, meaning the light bulb does not age or wear out. An old bulb is just as likely to break in the next second as a brand new one. This memoryless property defines the exponential distribution. To find the total accumulated risk, we set up the integral of the hazard function from time 0 to our target time t. Continuing with our calculation, integrating a flat constant is as simple as finding the area of a rectangle. The cumulative hazard function becomes 0.1 times t. This tells us the total accumulated danger grows in a perfectly straight line. Finally, we use our master formula, plugging in the negative cumulative hazard to find the survival function. The survival chance drops in a smooth curve known as exponential decay. If we plug in 10 years, we find the survival probability is about 36.8%. We have made a highly precise prediction from a very simple starting risk. Let us visualize exactly what we just calculated. On screen, you see 3 graphs that tell the complete story of our light bulb. The middle graph shows the hazard function, which is a perfectly flat horizontal line because the immediate risk never changes. Because of this constant risk, the bottom graph shows the cumulative hazard, growing as a perfectly straight, linear ramp, danger steadily piling up over time. Finally, the top graph shows the survival function. Driven by that accumulating risk, the probability of survival drops off in a smooth, sweeping exponential decay curve, starting at 100% and slowly approaching zero. Now let us look at a more realistic scenario. Human aging and mechanical wear and tear mean that the risk of failure usually increases as time goes on. Suppose a simplified model for a machine gives a hazard function of 2 times t. The older the machine gets, the more dangerous it becomes to operate. This growing risk is a simple version of a Weibull distribution. To find the total burden of wear and tear, we again set up the integral from 0 to t. But this time, because the risk is growing like a ramp, we are finding the area of a triangle, stacking increasing slices of risk. Continuing with our aging machine, solving this integral gives us a cumulative hazard equal to t squared. That exponent of 2 is incredibly important because it shows the total accumulated risk is accelerating. If you double the running time, the risk quadruples. Plugging this into our exponential survival formula, we get S of t equals the exponential of negative t squared. Because the time variable is squared inside a negative exponent, this survival curve drops off a cliff much faster than our light bulb. At just 2 years, the survival probability plummets to less than 2%, signaling to the engineer a critical need for early maintenance. Now that we have successfully used the master formula, let us understand where it comes from. We start with the fundamental theorem of calculus. The probability density function, f of t, is the negative derivative of the survival function. The rate of new failures equals the speed at which the surviving population shrinks. We substitute this derivative into our original hazard function definition. This gives us negative 1 over s of t times the derivative of s of t. In calculus, this specific fraction format perfectly matches the chain rule for the derivative of a natural logarithm. So the hazard function is exactly the negative rate of change of the log of survival. Continuing our derivation, we want to remove that derivative, so we integrate both sides from time 0 to t. Integrating the hazard function gives us the cumulative hazard function, capital H of t, on the left. On the right, the integral cancels the derivative, leaving just the negative natural logarithm of the survival function. We move the negative sign over, showing that total accumulated risk is directly proportional to the logarithm of your survival chance. Finally, to isolate the survival function, we apply the exponential function to both sides. And there we have it. The master formula is proven, directly linking accumulated risk to survival probability. We have covered the complete mathematical dashboard for analyzing lifespans. Remember the 3 main tools. The survival function tells us the overall probability of lasting past a certain time. The hazard function acts as a speedometer, measuring the immediate split-second risk of failure. And the cumulative hazard acts as an odometer, tracking the total accumulated danger over a lifetime. Through the master formula, these concepts unite, allowing us to predict the future of everything from human health in clinical trials to mechanical reliability in engineering with incredible precision. You now have a solid foundation in the functions of survival times.